When I first tried to build a recommendation system, I failed miserably. My algorithm suggested winter coats to customers in summer and sunscreen in winter. The problem wasn't my coding skills, it was my shallow understanding of probability. After years working with data science teams at tech companies, I've identified the exact probabilistic concepts that determine whether AI systems succeed or fail. Today, I'm sharing those concepts with you, along with the practical Python implementations that turn mathematics into working AI. Have you ever wondered why some AI systems make eerily accurate predictions while others fail completely? The contrast can be striking. One algorithm correctly identifies a rare disease from medical scans, while another autonomous vehicle misinterprets a white truck against a bright sky with tragic consequences. The difference often comes down to something most people don't immediately associate with artificial intelligence: probability mathematics. Modern AI systems aren't just collections of if-then statements or black box neural networks. At their core, they're sophisticated probability engines that quantify uncertainty and make decisions based on mathematical models of likelihood. This probabilistic foundation isn't just a technical detail, it's the beating heart of how machine learning actually works. When an AI system tells you there's a 92% chance of rain tomorrow, or recommends a movie you might like, it's making statistical inferences based on patterns in data. These predictions aren't magic, they're mathematical calculations rooted in probability theory. What's concerning, though, is the growing gap between implementation and understanding. A surprising number of data scientists and AI engineers are implementing sophisticated algorithms without grasping the probabilistic principles that make them work. A recent industry survey revealed that only about 30% of practitioners feel confident in their understanding of the probability models powering their systems. This knowledge gap isn't just an academic concern, it has real-world consequences. Consider what happens when probability is misunderstood or incorrectly implemented in critical systems. Autonomous vehicles have crashed because their perception systems miscalculated the probability of certain objects being present. Financial algorithms have caused flash crashes by incorrectly assessing the probability distributions of market movements. These failures aren't simply coding errors, they're fundamental misunderstandings of how probability should be modeled in complex systems. Probability serves as the translator between the messy, uncertain real world and the precise, deterministic nature of computers. Think about it. Humans naturally deal with uncertainty all the time. When you hear footsteps behind you, your brain automatically calculates the probability that it's a friend versus a stranger based on context, location, time of day, and countless other factors. Your decision to turn around or keep walking is informed by these probabilistic assessments. AI systems need a similar capability, but they can't rely on evolved intuition. Instead, they need mathematical frameworks that transform uncertainty into actionable predictions. That's where probability theory becomes essential. It provides the formal language that allows machines to reason about an uncertain world. The beauty of probability in machine learning is that it offers a unified approach to diverse problems. Whether we're teaching a computer to recognize faces, predict stock prices, or translate languages, the underlying mathematical principles remain consistent. This consistency allows us to build increasingly sophisticated AI systems on a solid theoretical foundation. So, what are these foundational principles? Three core probabilistic concepts underpin virtually all modern AI systems: conditional probability, Bayes' theorem, and probability distributions. Understanding these concepts isn't just helpful for theoretical knowledge. It's essential for building robust AI that won't mysteriously fail when deployed in the real world. Conditional probability addresses the relationship between events, how the probability of one outcome changes when we know another event has occurred. This concept is fundamental to classification tasks in supervised learning, where algorithms like logistic regression calculate the probability that a data point belongs to a specific category based on its features. When a spam filter evaluates an email, it's essentially calculating the conditional probability that the message is spam given the words it contains. Bayes' theorem provides a framework for updating beliefs based on new evidence, a process that lies at the heart of how machine learning models improve with additional data. This theorem connects prior knowledge with new observations, allowing AI systems to refine their understanding of the world incrementally. Probability distributions, meanwhile, allow us to model the entire range of possible outcomes and their likelihoods. In unsupervised learning, these distributions help identify patterns and structures in data without predefined labels. Clustering algorithms, for instance, build probabilistic models of how data points are distributed in space to identify natural groupings. The connection between these probabilistic concepts and actual machine learning approaches isn't merely theoretical. In supervised learning, we see probability theory at work when classification algorithms calculate the likelihood that an input belongs to different categories. A facial recognition system doesn't simply declare this is person X. It calculates probabilities for different identities and selects the most likely match based on mathematical rules. In unsupervised learning, probability plays an equally important role. When algorithms identify clusters in data or reduce dimensionality, they're essentially modeling the probability distributions that govern how data points are organized. These techniques allow us to discover hidden structures that might not be apparent to human observers. Throughout this video, we won't just discuss these concepts abstractly. We'll implement each probabilistic principle in Python code, showing you exactly how theoretical ideas translate into practical machine learning applications. You'll see how a few lines of code can transform raw data into probability values that enable accurate predictions. For conditional probability, we'll build a simple classifier that predicts outcomes based on feature values. For Bayes' theorem, we'll implement an algorithm that updates its beliefs as new data arrives. And for probability distributions, we'll write code that models complex patterns in real-world data sets. These implementations aren't just academic exercises. They're the building blocks of real AI systems that power technologies we interact with daily. By understanding the code behind these probabilistic techniques, you'll gain insights into how AI makes decisions and why those decisions sometimes go wrong. What makes conditional probability particularly powerful, and why it forms the foundation of machine learning, is that it allows algorithms to make predictions based on incomplete information. Just as humans can recognize a friend from a partial glimpse or identify a song from a few notes, machine learning systems can make accurate predictions with limited data by modeling conditional probabilities correctly. This capability mirrors human cognition in a profound way. When we navigate the world, we rarely have complete information about anything. Instead, we constantly make conditional inferences. Given what I can see, what's likely to happen next? Or, given these symptoms, what's the probable diagnosis? Machine learning algorithms formalize this intuitive process through mathematical models of conditional probability. The implications of this are far-reaching. By understanding how probability enables AI to function with incomplete information, we gain insights into both artificial and human intelligence. We see how mathematical frameworks can capture the essence of reasoning under uncertainty, a capability that defines intelligent behavior in any system, biological or artificial. Mathematical frameworks enable reasoning under uncertainty, but how exactly does an AI system calculate that a particular email is 95% likely to be spam just by analyzing its text? The answer lies in conditional probability, a concept so powerful that it allows machines to make surprisingly accurate predictions despite having only fragments of information to work with. When you check your email, you likely make split-second judgments about which messages are legitimate and which are spam. Your brain processes countless subtle clues, the sender's address, unusual phrasing, requests for personal information, all without explicitly calculating mathematical probabilities. Yet for AI systems to perform the same task, they need a rigorous mathematical framework to handle uncertainty. This is where conditional probability becomes essential. Conditional probability is expressed mathematically as PAB, which represents the probability of event A occurring given that event B has already happened. In more intuitive terms, it's how we adjust our beliefs about one thing when we learn something related to it. For spam filtering, this might be calculating P, spam contains free offer. The probability an email is spam given it contains the phrase free offer. This seemingly simple concept runs counter to our intuitions more often than we realize. Consider medical testing, where conditional probability reveals counterintuitive truths. Imagine a disease that affects 1% of the population and a test that's 95% accurate for both positive and negative results. If you test positive, what's the probability you actually have the disease? Many people intuitively answer 95%, but the correct answer using conditional probability is much lower, around 16%. This occurs because the rarity of the disease means false positives outnumber true positives, a calculation our brains rarely perform correctly without mathematical assistance. The Monty Hall problem provides another famous example of our flawed intuition about conditional probabilities. In this game show scenario, contestants choose one of 3 doors with a prize behind just one door. After making their selection, the host, who knows where the prize is, opens one of the other doors to reveal no prize. Should you stick with your original door or switch? Surprisingly, conditional probability tells us switching doubles your chance of winning from 1-3 to 2-3, a result so counterintuitive that even mathematicians initially disputed it. These examples highlight why we need formal mathematical approaches to conditional probability. Our intuitions often lead us astray, especially when probabilities need to be updated based on new information. For AI systems, conditional probability provides the foundation for making decisions with partial information. Consider facial recognition technology. When your phone attempts to recognize your face, it's not looking for an exact pixel-by-pixel match to a stored image. Instead, it calculates conditional probabilities. What's the likelihood this is person X given the specific facial features detected in the image? The system computes probabilities based on hundreds of measurements, distance between eyes, nose shape, jawline contours, to make its final determination. This approach makes facial recognition systems remarkably robust. They can still identify you when you're wearing glasses, sporting a new hairstyle, or standing in different lighting conditions because they're calculating probabilities based on the features they can detect, not requiring a perfect match. In classification algorithms like naive Bayes, conditional probability drives the entire prediction process. The algorithm looks at the conditional probability of each feature given a particular class, then combines these probabilities to predict the most likely class for new data. Despite its naive assumption that features are independent, often untrue in real data, this approach works surprisingly well for many applications, particularly text classification. Let's explore spam filtering as a concrete example. When an email arrives, a spam filter doesn't look for a single smoking gun to make its decision. Instead, it calculates the conditional probability of an email being spam given the words and phrases it contains. For example, if the word free appears in an email, what's the probability it's spam versus legitimate? To do this calculation, the filter needs training data, a collection of emails already labeled as spam or not spam. From this data, it calculates probabilities like P contains free. Spam. The probability that a spam email contains the word free. P contains free, not spam. The probability that a legitimate email contains free. It performs similar calculations for hundreds or thousands of words and phrases. When a new email arrives, the filter combines these conditional probabilities to determine whether the message is more likely spam or legitimate. This approach works because certain words appear with different frequencies in spam versus legitimate emails. Let's see how this works in practice with some Python code. Using NumPy, we can implement a simple conditional probability calculation. This simplified example shows how conditional probabilities transform raw data, word occurrences, into probability values that enable prediction. The code calculates how likely each word is to appear in spam versus legitimate emails, then uses those probabilities to classify a new message. In real-world implementations, these calculations would include prior probabilities, how common spam is overall, and would use logarithms to prevent numerical underflow when multiplying many small probabilities. The approach would also handle a much larger vocabulary and use techniques to deal with words never seen in the training data. What makes conditional probability so powerful for AI systems is how it quantifies uncertainty in a mathematically rigorous way. When an email filter marks a message as spam, it's not making a binary yes-no decision in isolation. It's calculating the probability based on patterns of word usage. This allows the system to express confidence levels, 95% likely to be spam, rather than just binary classifications. This capability to reason with uncertainty mirrors how humans make decisions in ambiguous situations. We rarely have complete information when making choices, yet we constantly assess probabilities based on partial evidence. Conditional probability gives machines this same ability to make educated guesses when certainty is impossible. While conditional reasoning helps machines make educated guesses with incomplete information, there's something even more remarkable about how today's AI systems continuously refine their predictions. When a doctor initially suspects pneumonia, but pivots to bronchitis after seeing lab results, they're performing an intuitive version of what mathematicians call Bayesian updating, the process of systematically revising beliefs when faced with new evidence. This ability to change course when new information arrives isn't just a human skill, it's a mathematical framework that transforms machines from static prediction engines into systems that grow increasingly accurate over time. That framework is Bayes' theorem, an elegant formula from the 18th century that has become the backbone of modern adaptive AI. To understand why this matters, consider what happens without Bayesian methods. Traditional systems often make rigid predictions based on initial statistical patterns they identify. When encountering situations that contradict their original model, they can't adapt, leading to predictions that become increasingly disconnected from reality. A weather forecasting system might continue predicting clear skies despite rapidly forming storm clouds if it lacks the mathematical framework to incorporate this contradictory evidence. At its core, Bayes' theorem is expressed as P, A, B, P, PBA, X, PA, PB. Though compact, this formula contains the essential components for belief updating. Let's break this down into its elements. PAB represents the posterior probability, what we want to know after seeing new evidence. Think of it as the updated belief. PA is the prior probability, our initial belief before seeing new evidence. This represents our starting point. PBA is the likelihood, the probability of observing the evidence if our hypothesis is true. This helps weigh how compatible the new evidence is with our current belief. PB is the marginal likelihood, the total probability of observing the evidence regardless of which hypothesis is true. This acts as a normalizing factor. Rather than remaining abstract, let's see this in action through a medical diagnosis example. Imagine an AI system screening for a rare disease affecting 1 in 1,000 people. When a patient tests positive on a screening that's 99% accurate, what's the probability they actually have the disease? Without Bayesian reasoning, we might wrongly assume the probability is 99%, but Bayes' theorem gives us the tools to calculate the correct answer. Our prior P disease is 0.0011 in 1,000. The likelihood P positive test disease is 0.99 test accuracy for true positives. To find P positive test, we need to consider all ways to get a positive result, either having the disease and testing positive, or not having it but getting a false positive. When we run the math, something surprising emerges. Despite the high test accuracy, the probability of actually having the disease after a positive result is less than 10%. This counterintuitive result demonstrates why Bayesian reasoning is so crucial. It prevents both humans and machines from dramatically overestimating probabilities based on partial evidence. The power of Bayes' theorem extends far beyond single calculations. Its real strength lies in iterative updating, starting with an initial belief and continually refining it as new evidence arrives. Each calculated posterior probability becomes the prior for the next round of updating, creating a feedback loop that gradually converges toward more accurate beliefs. This iterative process mirrors how humans learn from experience. We don't form permanent opinions after a single observation. We continuously refine our understanding as we gather more information. Bayesian updating gives machines this same ability, allowing them to start with imperfect knowledge and improve over time. In practical AI applications, this principle enables systems to adapt to changing conditions. A financial fraud detection algorithm might initially flag certain transaction patterns based on historical data, but as it processes more transactions and learns which alerts were false positives, it can recalibrate its detection thresholds through Bayesian updating, becoming increasingly precise in distinguishing between legitimate and fraudulent activities. The implementation of Bayesian methods in machine learning often takes the form of classifiers. For example, a naive Bayes classifier, despite its naive assumption that features are independent, proves remarkably effective for many real-world tasks. Let's see how this works in practice with a simple example in Python. What makes this approach powerful is that it's not just making predictions, it's calculating probabilities based on the principles of Bayes' theorem. For each new observation, the classifier computes the probability of it belonging to each possible class, then assigns it to the most probable class. When we run this on real datasets, we can observe a fascinating pattern. As more training data becomes available, the model's accuracy typically improves. This isn't just statistical averaging, it's Bayesian updating in action. The classifier is refining its understanding of the relationship between features and outcomes with each new example it processes. One common misconception about Bayesian methods is that they only work with complete information. In reality, the opposite is true. Bayesian reasoning shines brightest in scenarios with incomplete or uncertain data. When knowledge is partial, traditional statistical methods often falter, while Bayesian approaches can still provide meaningful probabilities by explicitly incorporating uncertainty. This characteristic makes Bayesian methods particularly valuable in fields like medical diagnosis, where decisions often must be made with limited information. A Bayesian medical system can start with general population statistics as priors, then update its assessment based on patient-specific symptoms, test results, and medical history, mimicking the diagnostic process of expert physicians. During the COVID-19 pandemic, Bayesian reasoning helped interpret test results by accounting for both test accuracy and local infection rates. In areas with low prevalence, even highly accurate tests produced significant numbers of false positives, a counterintuitive result that Bayes' theorem explains perfectly. The historical development of these methods is fascinating. While Thomas Bayes formulated his theorem in the 18th century, its full potential remained largely untapped until the computational revolution of the late 20th century. The iterative calculations required for complex Bayesian models were simply too cumbersome to perform manually. Today's computing power has removed this barrier, triggering an explosion in Bayesian applications across nearly every field of AI. What makes Bayesian updating particularly powerful is that it provides a principled approach to learning under uncertainty. Rather than arbitrary adjustments, it offers a mathematically sound method for incorporating new evidence, whether that evidence confirms or contradicts prior beliefs. This framework allows AI systems to not only make predictions, but also express appropriate confidence levels in those predictions, distinguishing between situations where they're nearly certain versus those where multiple interpretations remain plausible. We've explored how AI systems update their beliefs, but what exactly are they updating? Behind every AI prediction is a mathematical blueprint that maps all possible outcomes to their likelihoods, creating distinctive shapes that represent uncertainty. Did you know that just 4 mathematical patterns model most of the randomness in our world, from email frequency to financial markets? When we talk about uncertainty in AI, we're actually talking about specific mathematical functions called probability distributions. These aren't abstract concepts, they're precise mathematical tools that assign probability values to every possible outcome in a scenario. Think of them as the DNA of uncertainty, encoding the entire spectrum of possibilities into elegant mathematical patterns. While the math behind these distributions can be complex, their visual representations tell a compelling story. Each distribution creates a distinctive shape when graphed, revealing the underlying patterns of randomness at work. These shapes aren't just mathematical curiosities, they're the fundamental building blocks that allow AI systems to reason about uncertain events. In theory, these distributions appear as perfect, symmetrical curves on a mathematician's whiteboard, but in reality, AI systems must grapple with noisy, incomplete datasets that rarely match these idealized forms. The challenge lies in identifying which underlying distribution best explains the messy data we observe in the real world. It's like trying to recognize the outline of a mountain through fog and clouds. The perfect shape exists, but it's obscured by the noise and limitations of real-world measurements. Among the most important distributions in machine learning, the normal distribution reigns supreme. Often called the Gaussian distribution or simply the bell curve, it appears almost magically in countless natural phenomena, height distributions in a population, measurement errors in scientific experiments, and even the distribution of intelligence scores all tend to follow this symmetric, bell-shaped pattern. Its ubiquity in nature makes it an essential tool for AI systems that need to model continuous data clustered around a central value. The normal distribution's mathematical properties make it particularly useful in machine learning. Its shape is determined by just 2 parameters: the mean, average value, and standard deviation, measure of spread. This simplicity allows AI systems to efficiently characterize entire datasets with just these 2 numbers, creating a computational shortcut for modeling complex phenomena. But not all uncertainty follows the bell curve pattern. When all outcomes are equally likely, like rolling a fair die or selecting a random pixel from an image, we turn to the uniform distribution. This distribution creates a flat rectangular shape on a graph, representing scenarios where no particular outcome is more probable than another. AI systems often use uniform distributions for initialization steps or random sampling procedures where unbiased selection is crucial. For counting discrete events, like the number of successful conversions from an email marketing campaign, the binomial distribution becomes essential. It models scenarios with a fixed number of independent trials, each with the same probability of success. Its shape can range from symmetric to highly skewed depending on the underlying probability, making it adaptable to various real-world counting problems. Perhaps the most fascinating distribution for modeling real-world events is the Poisson distribution, which describes the number of events occurring within a fixed interval when these events happen at a constant average rate. It's particularly valuable for modeling phenomena like the number of emails arriving in an inbox per hour, customer arrivals at a service desk, or even the number of typing errors per page. The Poisson distribution's ability to model rare events with mathematical precision makes it invaluable for AI systems that need to anticipate infrequent but important occurrences. These mathematical patterns aren't just theoretical constructs. They're the foundation for how modern AI systems understand complex, uncertain environments. Consider a recommendation system suggesting products you might like. Behind the scenes, it's modeling your preferences using probability distributions, perhaps assuming a normal distribution of ratings for similar users or a Poisson distribution for purchase frequency patterns. Financial market analysis represents another domain where these distributions prove invaluable. While stock prices themselves rarely follow a perfect normal distribution, they tend to have fat tails indicating more extreme events than a normal distribution would predict. Many financial models use modified versions of these distributions to estimate everything from price movements to risk assessments. AI trading systems leverage these distributions to make split-second decisions worth millions of dollars. Even natural language processing relies heavily on these mathematical patterns. The frequency of words in a corpus often follows a Poisson distribution, while semantic similarities between words can be modeled using multidimensional normal distributions in vector space. These probabilistic foundations enable AI systems to generate coherent text and understand the nuances of human language. Implementing these distributions in code is surprisingly straightforward thanks to modern libraries. With just a few lines of Python using NumPy and Matplotlib, data scientists can generate and visualize these probability distributions. This simple code produces visualizations that reveal the characteristic shapes of each distribution, the symmetric bell curve of the normal distribution, the flat rectangle of the uniform distribution, and the asymmetric discrete pattern of the Poisson distribution. These visualizations help data scientists and AI engineers develop intuition about the underlying patterns in their data, but how do we determine which distribution best fits a particular data set? This is where techniques like maximum likelihood estimation come into play. This approach helps identify the parameters of a distribution that make the observed data most probable. In Python, libraries like SciPy make this process accessible. This code attempts to fit a normal distribution to data that actually follows a gamma distribution, a common scenario when working with real-world phenomena like wait times. The visual comparison quickly reveals whether the chosen distribution adequately captures the underlying pattern. In this case, highlighting the limitations of using a normal distribution for asymmetric data. For non-mathematicians, these visualizations transform abstract statistical concepts into intuitive shapes. They provide a visual language for understanding uncertainty, making probability theory accessible to a wider audience of AI practitioners who might otherwise struggle with the mathematical formalism. While visualizations make probability distributions accessible, they don't answer a fundamental question. How does AI determine which distribution best explains real-world data? Maximum likelihood. Estimation tackles this challenge by transforming the art of finding patterns into a precise science of optimization, one that powers everything from Netflix recommendations to financial forecasting models. When Netflix tells you that you're 87% likely to enjoy a new sci-fi series, or when Spotify suggests a playlist that seems to read your mind, these systems aren't just guessing. They're employing a powerful statistical method that finds the most probable explanation for the patterns in your behavior. This method is called maximum likelihood estimation, or MLE. At its core, MLE asks a deceptively simple question. Given all possible explanations or models for our data, which one makes our observations most likely to have occurred? Imagine you've collected data on how users rate movies. There are countless ways to model the relationship between user preferences and movie characteristics. Some models might emphasize genre, others might focus on actors, directors, or release year. MLE provides a systematic way to determine which model best explains the viewing patterns you've observed. The computational challenge here is immense. In theory, we're searching through an infinite space of possible distributions and parameter values to find the optimal explanation. It's like trying to find a specific grain of sand on all the beaches in the world. What makes this feasible is the mathematical elegance of the likelihood function. A likelihood function measures how well a particular statistical model explains the observed data. For any given model with specific parameters, the likelihood function calculates the probability that we would observe our actual data if that model were true. The higher this probability, the better the model fits our observations. In practice, working with the raw likelihood function can be computationally challenging, especially with large data sets. This is where log likelihood optimization comes in. By applying the logarithm to our likelihood function, we transform multiplicative operations into additive ones, making the calculations more manageable without changing which parameters maximize the function. This mathematical trick has made MLE practical for modern machine learning applications. The optimization process for finding these optimal parameters often employs sophisticated algorithms that efficiently search the parameter space. Python's scipy.optimize library provides powerful tools for this very purpose, allowing data scientists to define their likelihood functions and systematically search for the parameter values that maximize them. What's particularly fascinating about MLE is how it serves as the foundation for many supervised learning algorithms that might seem unrelated at first glance. When you train a linear regression model, the ordinary least squares method is actually equivalent to maximum likelihood estimation under the assumption that errors are normally distributed. Neural networks, despite their complexity, often use loss functions derived from MLE principles. Even common classification algorithms rely on maximizing the likelihood of the observed class labels given the features. Let's consider a concrete example. Imagine building a recommendation system. Your users rate movies on a scale from 1 to 5, and you want to predict how they'll rate movies they haven't seen yet. You might model each user's rating behavior as a normal distribution centered around their average rating, with some standard deviation representing how consistently they rate films. MLE can determine the specific parameters, mean and standard deviation, for each user that make their observed ratings most likely. The Python implementation might look something like this. You define a negative log likelihood function that calculates how well a particular set of parameters explains your data, then use scipy optimize to find the parameters that minimize this function, which is equivalent to maximizing the likelihood. The beauty is that once you have these optimal parameters, you can generate predictions by sampling from the resulting probability distribution. One of the trickiest aspects of implementing MLE involves balancing model complexity with accuracy. An overly complex model with too many parameters might fit the training data perfectly, but fail to generalize to new observations. A problem known as overfitting. MLE addresses this by naturally favoring simpler explanations when they adequately explain the data, embodying a statistical form of Occam's razor. This balance becomes evident when visualizing the optimization process. As model parameters are adjusted, the likelihood forms a landscape of peaks and valleys. The optimization algorithm climbs toward peaks, representing parameter values that make the observed data more likely. What's interesting is that sharper peaks correspond to more confident parameter estimates, while flatter regions suggest greater uncertainty about the optimal values. When working with high-dimensional data, such as user preferences across thousands of movies, the computational efficiency of MLE becomes critical. Modern implementations use various techniques to navigate these complex likelihood landscapes efficiently, from starting with educated guesses about parameters to employing adaptive step sizes during optimization. The sensitivity to initial parameter choices can present challenges, potentially leading the optimization to converge on locally optimal but globally suboptimal solutions. This is why data scientists often run MLE multiple times with different starting points, selecting the result that achieves the highest overall likelihood. What makes MLE particularly powerful is its versatility across different types of data and model structures. Whether you're modeling continuous variables like temperature readings, discrete counts like website visits, or binary outcomes like purchase decisions, MLE provides a consistent framework for extracting the most likely explanation from your observations. In recommendation systems, MLE excels at predicting user preferences by estimating the parameters of models that capture user behavior patterns. By analyzing your historical viewing or listening habits, these systems can identify the statistical patterns that best explain your choices and use those patterns to suggest content you're likely to enjoy. The percentage confidence values these systems display, 87% match, directly reflect the likelihood calculations derived from these optimized models. Beyond entertainment recommendations, MLE powers financial risk models, medical diagnosis systems, natural language processing, and image recognition algorithms. Anywhere patterns need to be discovered and quantified in data, MLE offers a rigorous mathematical approach for identifying the most likely explanation. From pattern recognition to mind reading, that's the true power of probabilistic machine learning in action. The same mathematical principles that help algorithms extract patterns from data are now enabling systems to predict what you'll want before you even know you want it. Have you ever wondered why Amazon's "you might also like" suggestions seem eerily accurate, or how streaming services manage to recommend your next favorite show with surprising precision? These recommendation systems represent one of the most tangible applications of the probabilistic concepts we've explored. By modeling the uncertainty in human preferences through sophisticated mathematical frameworks, these systems transform seemingly random user behaviors into predictable patterns that drive business decisions worth billions of dollars annually. The brilliance of recommendation systems lies in their ability to overcome three fundamental challenges that would otherwise make preference prediction nearly impossible. First, there's the sparse data problem. Most users interact with only a tiny fraction of available items. Imagine a streaming platform with 10,000 titles where the average viewer has only watched 50 shows. That leaves 99.5% of potential user item interactions unknown, creating a vast sea of uncertainty. Second, there's the cold start problem. How do you make recommendations for new users with no history or new items with no interactions? Without prior data to establish conditional probabilities, traditional statistical approaches would fail completely. Third, there's the challenge of shifting preferences. Humans are notoriously inconsistent, with tastes that evolve over time. The documentary you enjoyed last month might have little bearing on what you'll want to watch tonight after a stressful day at work. Probabilistic models offer elegant solutions to these seemingly insurmountable challenges. Let's explore how they work in practice. Collaborative filtering stands as one of the most powerful approaches in recommendation systems. Rather than trying to understand the intrinsic qualities of items, it leverages the wisdom of the crowd through conditional probabilities. The core insight is beautifully simple. If person A and person B have historically enjoyed many of the same products, there's a higher probability that person A will like something person B recently enjoyed. This approach transforms the sparse data problem from a limitation into a strength. By modeling similarity between users, the system can make informed predictions even when direct evidence is lacking. It's akin to asking your friend with similar taste for recommendations, except the algorithm can analyze millions of friendships simultaneously. The mathematical implementation relies on conditional probabilities to quantify the likelihood of a user enjoying an item given their past behavior and the behavior of similar users. If 80% of users who watched both Stranger Things and Dark also enjoyed Black Mirror, the system can calculate a high probability that you'd enjoy Black Mirror if you've watched the other two shows. While collaborative filtering leverages user similarities, content-based filtering takes a different probabilistic approach. It models user preferences across specific attributes of items using probability distributions. For example, a streaming service might analyze that your viewing history shows a normal distribution centered around science fiction from the 2010s with female leads and dystopian themes. This approach creates a probabilistic profile of your preferences across multiple dimensions, allowing the system to recommend new content that matches this profile, even if no other user has made the same connections. The system essentially builds a probability distribution of your preferences across various features and uses this to calculate the likelihood you'll enjoy new items. What makes content-based filtering particularly powerful is its ability to handle the cold start problem for new items. Even if nobody has watched a newly added documentary, the system can analyze its attributes and match them against user preference distributions to make informed recommendations from day one. Matrix factorization represents a more sophisticated probabilistic approach that addresses both the sparsity and dimensionality challenges of recommendation data. Rather than working with explicit user and item features, it discovers latent factors, hidden dimensions that explain patterns in user-item interactions. This technique decomposes the sparse user-item interaction matrix into two lower dimensional matrices, one representing users and one representing items. These matrices capture the underlying patterns in the data, effectively reducing dimensionality while uncovering hidden relationships. Each user and item is represented as a vector in this latent space, with the probability of a user liking an item determined by how closely their vectors align. What's fascinating about matrix factorization is that the discovered latent factors often correspond to interpretable characteristics, like genre preferences or production quality, even though the algorithm was never explicitly told about these attributes. The system learns these probabilistic patterns purely from observing user behavior. Implementing these concepts in Python is surprisingly accessible thanks to libraries like scikit-learn. With just a few dozen lines of code, we can build a recommendation system that combines these probabilistic approaches. The implementation typically involves pre-processing user-item interaction data, training a model using one or more of the techniques we've discussed and generating personalized recommendations based on calculated probabilities. Let's consider a practical example. When an e-commerce platform implements these techniques, the results can be transformative. By accurately modeling the conditional probabilities of user preferences, recommendation systems have been shown to drive significant increases in engagement, satisfaction, and ultimately revenue. The evaluation of recommendation systems introduces another layer of probabilistic thinking. Metrics like precision, what percentage of recommended items were actually relevant, and recall, what percentage of relevant items were actually recommended, are fundamentally probabilistic measures. They help quantify how well the system's probability estimates match actual user preferences. What's particularly fascinating is how these systems balance exploration and exploitation, another probabilistic concept. While the system wants to recommend items with the highest probability of user enjoyment, exploitation, it also needs to gather information about user preferences for unfamiliar categories, exploration. This represents a classic probability problem known as the multi-armed bandit problem, where the system must balance certain short-term rewards against potentially larger long-term gains from exploration. The most sophisticated recommendation systems go beyond simple collaborative or content-based filtering. They employ ensemble approaches that combine multiple probabilistic models, each capturing different aspects of user preferences. By weighting and integrating these models, the system can generate recommendations that account for both the wisdom of similar users and the specific content attributes that align with an individual's taste profile. These systems also adapt over time using Bayesian updating principles. As users interact with recommendations, either positively or negatively, the system updates its probability estimates accordingly. If you skip through 3 consecutive comedy specials that were recommended to you, the system will reduce the probability estimate for your interest in that genre and adjust future recommendations accordingly. The practical impact of these probabilistic approaches extends far beyond entertainment. The same techniques power product recommendations in e-commerce, job suggestions in professional networks, friend recommendations in social media, and even potential matches in dating applications. In each case, the core challenge remains the same: modeling human preferences under conditions of extreme uncertainty. Uncertainty doesn't just exist in human preferences, it's the constant companion of every autonomous vehicle on the road. When a self-driving car encounters dense fog that obscures its cameras or urban canyons that block GPS signals, it doesn't simply stop operating. Instead, it leverages sophisticated probabilistic techniques that transform a cloud of uncertainty into confident navigation decisions. This represents one of the most consequential applications of probability theory, where algorithms must continuously answer the question, where am I and what's around me, based on incomplete and often contradictory information. Unlike recommendation systems that model preferences in digital spaces, autonomous vehicles operate in physical environments where miscalculations can have immediate and potentially fatal consequences. A movie suggestion algorithm that's 80% accurate might slightly annoy users, but a self-driving car that's 80% certain about the location of a pedestrian creates an unacceptable safety risk. The fundamental challenge faced by autonomous vehicles is navigating through a world of partial observability. Imagine driving through a tunnel where your GPS signal disappears, visibility is limited, and sensors become less reliable. Human drivers naturally compensate by relying on their last known position, tracking lane markings, and making educated guesses. Autonomous vehicles must replicate this intuitive reasoning through mathematical frameworks that quantify uncertainty. This is where Bayesian filtering methods become essential. These probabilistic techniques help autonomous vehicles maintain a reliable estimate of their position even when sensor data becomes unreliable or contradictory. The two most important implementations are Kalman filters and particle filters, each serving crucial but distinct roles in autonomous navigation. Kalman filters excel at tracking dynamic systems through noisy measurements. They maintain two key pieces of information: the estimated state, like position and velocity, and the uncertainty in that estimate. What makes them particularly valuable for autonomous vehicles is their ability to fuse data from multiple sensors while accounting for the reliability of each. When a GPS reading arrives, the filter weighs it against its current position estimate, giving more influence to the more certain information source. For example, when a vehicle travels through an urban canyon where tall buildings reflect GPS signals, the Kalman filter detects the increased uncertainty in those readings and relies more heavily on other sensors like wheel encoders or inertial measurement units. As the vehicle emerges into open space with clear GPS reception, the filter automatically shifts to trust the now accurate GPS data more heavily. Particle filters take a different approach that's particularly useful in complex environments. Rather than maintaining a single state estimate with an uncertainty measure, they represent the vehicle's possible states as a collection of particles, each representing a hypothesis about the vehicle's true position. As new sensor data arrives, particles that align with that data receive higher weights, while inconsistent particles are gradually eliminated. This approach allows autonomous vehicles to maintain multiple hypotheses simultaneously. When a vehicle approaches an intersection with similar-looking buildings on each corner, the particle filter might maintain 4 clusters of particles, each representing a possible orientation. As the vehicle gathers more information, perhaps recognizing a distinctive landmark, the particles representing incorrect hypotheses fade away, leaving only those that match reality. The practical implementation of these filters involves sophisticated mathematical operations, but we can understand the core principles through a simplified example. Consider an autonomous vehicle traveling down a straight road with access to two information sources: a GPS sensor that provides absolute position but with substantial noise, and wheel encoders that track relative movement accurately but accumulate errors over time. In Python, we might implement a basic version of a Kalman filter to fuse these data sources. This simplified implementation demonstrates how the filter balances its trust between different information sources based on their reliability. The resulting visualization would show the true position, noisy GPS readings, and the filtered position estimate that smoothly follows the true trajectory despite significant noise in the raw measurements. The brilliance of this approach becomes apparent when we consider that real autonomous vehicles must integrate dozens of sensors: cameras, LiDAR, radar, GPS, wheel encoders, inertial measurement units, each with different error characteristics and update frequencies. Probabilistic filtering creates a coherent understanding from this cacophony of data. Beyond positional tracking, conditional probability plays a crucial role in object detection and classification. When an autonomous vehicle's sensors detect something in its path, it must determine what that object is to respond appropriately. Is it a pedestrian about to cross, a paper bag blowing across the road, a lane marking? Each classification leads to a different response. Modern autonomous vehicles use probability distributions to represent their confidence in different classifications. Rather than simply deciding this is a pedestrian, they might calculate that an object has a 97% probability of being a pedestrian, 2% probability of being a cyclist, and 1% probability of being something else. This nuanced understanding allows the vehicle to make appropriate risk-weighted decisions. The uncertainty in these classifications isn't a weakness. It's a strength that allows autonomous systems to make rational decisions in ambiguous situations. By maintaining explicit probability distributions rather than making premature classifications, the vehicle can act conservatively when facing high-risk uncertainties, slowing down when unsure if an object is a pedestrian, while proceeding normally when uncertainties are low risk. These probabilistic techniques become especially important when dealing with sensor fusion. Each sensor has blind spots and failure modes, but probabilistic models can integrate their complementary strengths. Cameras provide rich visual information but struggle in low light. Radar penetrates fog but gives less detailed shapes. LiDAR offers precise 3D mapping but can be confused by reflective surfaces. By modeling the uncertainty characteristics of each sensor, the vehicle can maintain reliable perception even when individual sensors fail. One of the most compelling demonstrations of probabilistic robotics is watching the uncertainty visualization of a vehicle's position estimate. Initially, when a vehicle is first activated, its position estimate might show a wide Gaussian distribution across a large area. As it begins to move and collect sensor data, this distribution narrows dramatically, concentrating around the true position. Additional sensory landmarks further constrain the distribution until the vehicle achieves centimeter-level positioning accuracy. The real-world impact of these techniques can't be overstated. When an autonomous vehicle navigates through a construction zone where lane markings have been altered, probabilistic methods allow it to maintain orientation by tracking consistent landmarks like buildings and trees. When GPS signals bounce off buildings in urban environments, creating position jumps of hundreds of meters, these same methods reject the outliers and maintain a stable trajectory. While autonomous vehicles navigate the physical world using probability, language models like ChatGPT face an equally complex challenge, making sense of human communication. When you interact with an AI assistant, you're witnessing probability in action with every word it generates, though the mathematics happens beneath the surface, hidden from view. Natural language is arguably humanity's most sophisticated invention, a system with countless subtle rules, exceptions, regional variations, and contextual nuances. The average English speaker knows around 40,000 words, each of which could potentially follow any other. This creates a vast landscape of possibilities that seems impossible to navigate without genuine understanding. Yet today's language models generate remarkably coherent text without comprehending a single concept they discuss. How is this possible? The answer lies in treating language itself as a probability problem. Rather than trying to program rules of grammar or define the meaning of words, modern NLP approaches the challenge by asking, given the previous words in this sequence, what word is most likely to come next? This seemingly simple question turns out to be extraordinarily powerful. The earliest attempts at this probabilistic approach were n-gram models. An n-gram is simply a sequence of n adjacent words from a text. A bigram model, where n2 looks at pairs of words, while a trigram model examines sequences of 3 words. These models calculate conditional probabilities. If you've just seen the words the red, what's the probability that car comes next versus house or apple? Let's consider how this works in practice. Imagine we're building a simple predictive text system using a bigram model. If we analyze a large corpus of text, we might discover that after the word despite, the word the appears 30% of the time, his appears 15% of the time, and so on. When a user types despite, our model can suggest completions based on these probabilities. This approach requires no understanding of what despite actually means. It's purely statistical. The model doesn't know that despite indicates a contrast or that it requires a noun phrase to follow. It only knows the statistical patterns it observed in its training data. N-gram models were revolutionary but limited. They struggle with long-range dependencies, connections between words that are far apart in a sentence, and have no concept of semantic meaning. Imagine trying to predict the final word in "The man who walked into the store bought a tea Torkheim. A Bigram model only sees bought A and might suggest car, but the full context makes sandwich more likely if the store is a deli. Bayesian methods expanded the capabilities of language models by allowing them to incorporate prior knowledge and update predictions based on new evidence. In sentiment analysis, for instance, Bayesian classifiers calculate the probability that a text expresses positive or negative sentiment based on the words it contains. The analysis doesn't understand emotions. It only knows that words like excellent frequently appear in positive reviews, while words like disappointing are common in negative ones. Topic modeling is another powerful application of Bayesian methods in NLP. Algorithms like Latent Dirichlet Allocation, LDA, can discover hidden topics in large document collections by modeling the probability distributions of words across topics. When applied to news articles, for example, LDA might identify clusters of words related to politics, sports, technology, and entertainment without any prior knowledge about these categories. The true revolution in NLP came with the introduction of word embeddings and neural language models. Word embeddings transform words into vectors in a high-dimensional space where semantically similar words cluster together. Instead of treating dog and puppy as completely unrelated tokens, embeddings capture their relationship by positioning them near each other in vector space. Modern language models like transformers, the architecture behind GPT and BERT, use probability distributions over these word embeddings to generate text. When generating the next word, a transformer isn't simply picking the single most likely candidate, it's sampling from a probability distribution of possible words, which allows for creativity and variation in its outputs. What's fascinating is that we can implement a simple probabilistic text generator with just a few dozen lines of Python code. Using libraries like NumPy, we can create a model that predicts the next word based on probabilities derived from a training corpus. When we test this model on different text corpora, the results are illuminating. Training it on Shakespeare produces text with archaic sentence structures and vocabulary. Training on modern news articles generates more contemporary language. Training on technical documentation yields specialized terminology. In each case, the model captures the statistical patterns of language without understanding a word of what it's generating. The evaluation of these language models often uses metrics like perplexity, which measures how well a probability model predicts a sample. Lower perplexity indicates better predictive performance, reflecting the model's ability to assign higher probabilities to the correct next words, essentially quantifying how surprised the model is by the actual text. We can visualize the probabilistic nature of language modeling through word clouds or probability distributions that show the frequency and likelihood of word occurrences. These visualizations help us understand how language models think about word relationships and make predictions. What's most remarkable about this approach is that by treating language as a probability problem, machines can generate text that passes for human-written without possessing anything resembling comprehension. A language model doesn't know what umbrella means or why you might need one when it's raining. It only knows the statistical pattern that "I forgot my" is often followed by umbrella when the context includes words like rain or storm. This probabilistic foundation explains both the impressive capabilities and the strange limitations of modern language models. They can write essays, poems, and code that seem to demonstrate understanding, but occasionally produce nonsensical outputs that reveal their lack of true comprehension. They're essentially sophisticated pattern-matching systems operating on probability distributions rather than meaning. Pattern matching based on probability distributions isn't just powering text generation, it's enabling machines to imagine. What happens when AI learns not just to recognize patterns, but to create new variations that follow those same statistical rules? The answer lies in generative models, which have quietly sparked a revolution in how machines can extend human creativity. Imagine scrolling through a gallery of portraits and discovering that none of the people actually exist. Each face, with its unique wrinkles, asymmetries, and expressions, was created by an AI system that learned the probability distribution of human facial features. This isn't science fiction. It's happening right now with generative AI that can produce stunningly realistic images, music, videos, and more. Unlike the discriminative models we've discussed previously, generative models serve a fundamentally different purpose. Rather than focusing on classifying or predicting outputs based on inputs, these models learn the underlying joint probability distribution of the data itself. This mathematical distinction allows them to perform what seems like magic, creating entirely new samples that follow the same statistical patterns as their training data. The challenge these models face is immense. Consider a typical 1080p image. It contains over 2 million pixels, each with its own color value. The probability space of all possible images at this resolution is astronomically vast, with most combinations resulting in pure visual noise. Yet within this near-infinite space exists a tiny subspace of images that humans would recognize as coherent: faces, landscapes, animals, and other familiar scenes. This is where the probabilistic foundation becomes critical. Generative models must somehow learn the complex probability distribution that describes the subspace of realistic images, capturing intricate dependencies between pixels. It's like finding a needle in a haystack the size of the universe. Variational autoencoders, VAEs, were among the first modern approaches to tackle this challenge. These models employ a clever probabilistic trick. They compress input data into a latent space where each point represents a probability distribution rather than a fixed value. This compressed representation captures the essential statistical properties of the training data. The variational aspect comes from approximating complex probability distributions with simpler ones that are easier to work with mathematically. When a VAE encodes an image of a face, it doesn't map it to a single point in latent space, but rather to a distribution, typically a Gaussian with a mean and variance. This probabilistic encoding allows for smooth interpolation between different faces and enables the generation of new unseen variations. To generate a new image, the VAE samples from this latent distribution and passes it through a decoder network. The resulting output won't be an exact copy of any training image, but rather a novel sample that reflects the statistical patterns the model has learned. It's as if the model is saying, based on all the faces I've seen, here's what another plausible human face might look like. While VAEs offer an elegant probabilistic framework, their outputs often lack the sharp detail of real images. This limitation led to the development of generative adversarial networks, GANs, which take a completely different approach to the same problem. GANs introduce a fascinating competitive dynamic between two neural networks. The generator network attempts to create realistic outputs, while the discriminator network tries to distinguish between real training data and the generator's creations. This adversarial setup creates a feedback loop where both networks continually improve, the generator learning to create increasingly convincing fakes, and the discriminator becoming more discerning in spotting them. This process resembles a counterfeiter and detective locked in an eternal duel, each forcing the other to improve. The probabilistic foundation appears in how the discriminator outputs a probability judgment. There's a 92% chance this image is real. The generator's goal is to maximize this probability, essentially trying to fool the discriminator into assigning high probabilities to its generated samples. The most recent breakthrough in generative modeling comes in the form of diffusion models, which apply Bayesian principles in yet another innovative way. These models work by gradually adding noise to training images until they become pure randomness, then learning to reverse this process. By starting with random noise and iteratively removing it according to learned patterns, diffusion models can generate remarkably detailed and coherent images. This approach has several probabilistic advantages. By framing image generation as a gradual denoising process, diffusion models can better capture complex dependencies between different parts of an image. The step-by-step nature also allows more stable training compared to GANs, which can suffer from instability as the generator and discriminator compete. Let's see how we might implement a simple variational autoencoder in PyTorch. This code demonstrates the probabilistic nature of VAEs. The reparameterize function is where the magic happens. It samples from the learned probability distribution in the latent space using what's called the reparameterization trick. This allows the model to maintain differentiability while incorporating randomness, enabling it to learn through standard backpropagation. One of the most fascinating aspects of generative models is visualizing their latent space, the compressed representation where different regions correspond to different types of outputs. By plotting this space and sampling from different regions, we can see how the model organizes its learned probability distribution. For instance, in a VAE trained on face images, moving gradually from one point to another in latent space creates a smooth transition between different faces. Move in one direction, and faces might become more feminine. Move in another, and they might age. This latent space visualization reveals that the model hasn't just memorized training examples, it's learned an underlying probabilistic structure that captures meaningful variation in the data. The ethical implications of these models are profound. Their ability to generate convincing fake content raises serious concerns about deepfakes and misinformation. When an AI can generate a realistic video of a public figure saying something they never said, or create convincing but fictional news articles, the line between real and artificial becomes dangerously blurred. This is the double-edged sword of generative AI. The same probabilistic principles that enable creative applications also enable potential misuse. Despite these concerns, generative models represent the culmination of probabilistic machine learning, systems that don't just analyze existing patterns, but create new variations that follow the same statistical rules. They've moved AI from the realm of pattern recognition to pattern creation, from understanding to imagination. As we've moved from understanding to imagination with generative models, a critical question emerges that haunts both beginners and experts alike. Faced with a new machine learning problem, how do you determine which probabilistic framework to apply? The reality is that up to 80% of failed AI projects stumble not during implementation, but during this critical initial decision point. Even with cutting-edge algorithms at your disposal, selecting the wrong probabilistic approach can lead to months of wasted effort and resources. Think about it this way. Probabilistic machine learning is like having a workshop full of specialized tools. Each tool, whether it's a Bayesian classifier, a generative model, or a maximum likelihood estimator, was designed to solve specific types of problems. Using the wrong tool not only makes the work harder, but can make success impossible regardless of your expertise or the quality of your data. Let's build a practical decision framework that will help you systematically select the right probabilistic approach for any AI challenge you encounter. This isn't about memorizing algorithms. It's about understanding the underlying principles that guide your choices. First, we need to determine whether your problem is fundamentally supervised or unsupervised. In supervised learning, you're working with labeled data and trying to learn a mapping from inputs to outputs. The probabilistic question here is, what is the conditional probability of the output given the input? This is where techniques like logistic regression, support vector machines, and neural networks shine. In contrast, unsupervised learning deals with unlabeled data where you're trying to discover, hidden patterns or structures. Here, the probabilistic question shifts to: what is the joint probability distribution that could have generated this data? This is the domain of clustering algorithms, dimensionality reduction techniques, and the generative models we discussed earlier. But the supervised versus unsupervised distinction is just the first fork in our decision tree. Let's go deeper. If you're dealing with a supervised problem, are you looking at a classification task, predicting discrete categories, or a regression task, predicting continuous values? Classification problems typically benefit from discriminative models that focus directly on decision boundaries between classes. These models estimate the conditional probability of class membership given the features. For example, when building a fraud detection system, a discriminative approach would directly model the probability of a transaction being fraudulent based on its characteristics. It doesn't waste computational resources modeling how legitimate transactions are generated. It focuses solely on the decision boundary. Regression problems, on the other hand, might benefit from approaches that model the full probability distribution of the target variable. This allows you to quantify uncertainty in your predictions, which is crucial in fields like financial forecasting or medical prognosis, where knowing the confidence interval of a prediction can be as important as the prediction itself. For unsupervised problems, the nature of your data and your objectives will guide your choice. Are you looking to reduce dimensionality while preserving statistical relationships? Principal component analysis offers a probabilistic interpretation where components capture maximum variance. Are you trying to discover discrete groups within your data? Gaussian mixture models provide a probabilistic approach to clustering that can handle overlapping clusters. Now, let's address a crucial consideration that's often overlooked: the amount and quality of data you have available. Probabilistic techniques aren't equally data hungry. Some approaches, particularly complex generative models, require massive data sets to accurately estimate probability distributions. Others, like Bayesian methods, can perform reasonably well with smaller data sets by incorporating prior knowledge. If you're working with limited data, techniques that allow you to explicitly incorporate domain knowledge through priors can be invaluable. This is where the generative discriminative distinction becomes practical. Generative models which learn the joint probability distribution typically need more data, but can handle missing values and incorporate prior knowledge more naturally. Discriminative models focusing only on the conditional probability are often more efficient with data but may struggle with incomplete information. The nature of uncertainty in your problem should also influence your choice. Is the uncertainty primarily aleatoric, inherent randomness in the system, or epistemic, uncertainty due to limited knowledge? Bayesian approaches excel at quantifying epistemic uncertainty, which can be reduced with more data. Traditional maximum likelihood methods might underestimate uncertainty by not accounting for parameter uncertainty. Let's make this concrete with an implementation checklist for your probabilistic machine learning projects. 1. Define your problem precisely. Is it supervised or unsupervised? Classification or regression? What type of uncertainty matters most? 2. Inventory your data. How much do you have? What's the quality? Are there missing values? Do you have domain expertise that could inform priors? 3. Match the problem characteristics to appropriate probabilistic techniques. Use generative models when modeling the full data distribution is important. Use discriminative models when efficiency and prediction accuracy are paramount. 4. Structure your model. Clearly define all parameters and assumptions. This transparency will be crucial for evaluation and communication later. 5. Implement robust validation strategies. Cross-validation for supervised problems held out likelihood estimation for unsupervised ones. 6. Evaluate uncertainty explicitly. Don't just look at point predictions, examine confidence intervals, prediction intervals, or credible intervals depending on your approach. 7. Communicate results clearly. Different stakeholders need different levels of detail about the probabilistic nature of your results. Speaking of communication, this is where many probabilistic projects falter despite solid technical implementation. When presenting probabilistic results to non-technical stakeholders, remember that probability is counterintuitive for most people. Simply stating that a model is 80% confident in a prediction often leads to misinterpretation. Instead, use visualizations to represent uncertainty. Confidence bands around forecasts, color-coded risk maps, and alternative scenario comparisons can make probabilistic concepts more intuitive. Always provide context for what the probabilities mean in practical terms. Translate 80% probability of rain into you'll very likely need an umbrella today. It's also essential to clearly explain the underlying assumptions of your model. Every probabilistic approach makes assumptions about data distributions, independence of variables, or stationarity over time. When these assumptions are violated, predictions can become unreliable. Being transparent about these limitations builds trust and leads to better decision-making. Consider this example. If you're building a recommendation system, you might find that collaborative filtering approaches work well for users with substantial history, but perform poorly for new users. A hybrid approach using content-based methods for new users and collaborative filtering for established ones might be optimal. This nuanced implementation comes from understanding the probabilistic strengths and weaknesses of each approach. When evaluating uncertainty in your models, pay special attention to calibration, how well your probability estimates match empirical frequencies. A well-calibrated model that predicts a 70% chance of an event should be correct roughly 70% of the time. Calibration plots can help identify whether your model is overconfident or underconfident in different regions of the probability space. For complex, high-stakes decisions, consider ensemble methods that combine multiple probabilistic approaches. This not only improves accuracy, but can provide more robust uncertainty estimates. When different models with different assumptions agree on a prediction, you can have greater confidence in the result. Remember that dealing with incomplete data is a common challenge in real-world applications. Probabilistic approaches offer principled ways to handle missing data through techniques like multiple imputation or by directly modeling the missing data mechanism. Choose approaches that can robustly deal with the data quality issues you expect to encounter. Finally, ensure your model generalizes well to unseen data. Overly complex models might capture noise in your training data rather than genuine patterns, leading to poor performance in production. Regularization techniques informed by probabilistic principles can help prevent this overfitting. And there you have it. The common thread running through every breakthrough AI system we've explored is a foundation in probability. It's not just abstract mathematics, but the essential language that allows machines to make sense of our uncertain world. As one leading AI researcher put it, the language of probability and uncertainty is built on a few crucial concepts such as entropy and KL divergence, which are fundamental to advancements in modern machine learning. As you apply these concepts to your own projects, remember to start simple before building complexity. For continued learning, explore interactive resources on platforms like Brilliant that offer lessons on probability and data analysis tailored to machine learning applications. Your journey toward AI mastery begins with probability, not just understanding algorithms, but truly grasping the mathematics of uncertainty that powers them.